So I will present a talk on optical frequency comms, unlocking a high precision optical sensing and advanced imaging. Go to introduction. Let's start my talk from the difference between the laser and the optical frequency comm. Optical cavity has a gain medium and a pair of cavity mirrors. Lights go back and forth inside. Only the optical standing wave survives, and a portion of it is leaked from the cavity mirror with a low transmittance. If only one wave survives, we get a single wavelength laser. It gives a sine wave in time and one line in the spectrum. If so, we have two waves, we get a two wavelengths laser or dual wavelength laser giving an optical bit signal in time and two line in the spectrum. Optical frequency comm has many wavelengths, like tens of thousands. In time, it makes an ultra-short pulse. In frequency, we see an array of phase-locked narrow line space at the equal interval. Why so the optical comm creates an ultra-short pulse in the time domain? The key is overlaying the tens of thousands of optical wavelengths in phase. Each color has a different wavelengths, like here. But if so, we align their phase at one moment in time, like here, the interference is constructively. This creates a strong pulse. And between the pulses, the interference is destructive. So we get a train of ultra-short pulses. However, if we add the same wavelengths with a random phase relationship, they don't combine into the pulse. The result is just a random light. Let me explain the relationship between the ultra-short pulse train and the optical comm. Inside the laser cavity, an ultra-short pulse goes back and forth. Each time it completes one round trip, one pulse leaked out. This forms a train of ultra-short pulses. If the cavity length is L, the pulse period T is given by these equations. Now let's look at this in the frequency domain using a Fourier transform. This results a spectrum of discrete lenses, namely optical comm. The spacing between the comm line is the inverse of pulse period of T. The spectral bandwidth depends on the pulse duration. Shorter pulse gives a broader spectra. An optical comm is equivalent to the tens of thousands of stable CW lasers in a single device. In this way, the ultra-short pulse train and frequency comm are connected. So what makes the optical comm unique? The answer is optical spectrum. Broad blackbody radiation, such as sunlight, has a continuous spectrum with a broad bandwidth, like here. This means it covers many wavelengths, but without a sharp structure. On the other hand, the atomic clock emission shows the discrete spectrum with a narrow line width at a specific wavelengths, but its wavelength is localized and limited. Now look at the optical comm. It is special because it has a discrete spectrum, broad bandwidth, and equal space line. So the optical comm combines the feature of blackbody radiation and atomic emission, namely broadband bandwidth and discrete spectrum. And most importantly, equally spaced lines are unique to the optical frequency comm. One representative application of OFC is a ruler for the optical frequency. OFC is composed of series of frequency spikes regularly separated by a constant frequency. and has a both feature of narrow line width and the broad spectral coverage together with a constant frequency spacing. The most important characteristics of OFC is given by this simple equation, where the nu m is the optical frequency of each OFC mode. FCO is a carrier envelope offset frequency, FREP is the frequency spacing, and M is the number of OFC mode. Since FCO and FREP are photonic radio frequency signal around several tens megahertz, this equation indicates a coherent link of frequency between the optical and electric region. For example, if the FCO and the FREP are phase locked to an electric frequency standard by laser control, uncertainty of the frequency standard can be transferred to the nu m based on this equation. So in this case, the OFC can work as an optical frequency ruler secured by the electric frequency standard. This approach revolutionized the field of optical frequency and metrology. Optical frequency metrology such as optical spectroscopy and the optical frequency standard, leading to the Nobel Prize in Physics 2005. For example, the optical comb can be used as a spectral ruler for reading the gas absorption line. When the comb passes through a gas, the gas absorbs the light at specific wavelengths. This generates a dip in the comb spectrum. Right at the position of the gas absorption line, we can easily read this absorption using an evenly spaced comb line as a scale. With an optical comb, we can perform the gas spectroscopy with a high resolution, broad spectral bandwidth, absolute frequency measurement, and high-speed data acquisition. Therefore, this makes it optimal for the rapid monitoring of environmental gases. Next slide shows an example of simultaneous analysis of mixed gas. Here, the gas like water vapor, acetylene, and methane can all be measured in a single shot. Each gas shows a unique absorption feature, and the comb spectra can capture all of them together. Recently, the optical frequency standard, with a much better performance than the electric frequency standard, appears, like an optical atomic clock and optical lattice clock. In this case, if the nu m is phase locked to an optical frequency standard by laser control, excellent uncertainty of the optical frequency standard can be transferred to the electric signal of FREP based on this equation. So, in this case, the OFC can work as a frequency converter or frequency gear from optical to electric field. Therefore, OFC can be used for the generation of ultra-stable or electric wave in RF, microwave, and millimeter wave and terahertz wave. Importantly, so such an electric signal is synthesized from the optical frequency standard via the optical comb. We apply this application for the photonic terahertz generation by photomixing of a microcavity comb or microcomb. Microcomb generates OFC with FREP over several hundred gigahertz, which is comparable to the 60 wireless carrier frequency. Optical bandpass filter extracts the two adjacent OFC mode from the microcomb, so the new one and the new to right, with the frequency spacing of FREP. A pair of new one and new to right generates optical bit signal in time domain. The bit frequency or envelope frequency is exactly equal to FREP. Then the optical bit signal is converted into terahertz wave by a photomixer such as a UTC-PD. The resulting terahertz wave has a frequency of f terahertz, which is exactly equal to f-rep. In this way, the low phase noise property of f-rep in the microcomb can be transferred to the terahertz wave. We use this terahertz wave for the terahertz carrier generation and the wireless communication at the 560 gigahertz band. Upper shows the experimental setup, including 4 keys. The first key is a microcomb for the generation of low phase noise terahertz wave. Second key is optical injection locking for optical amplification without the dual wavelength optical carrier for photomixing without the ASE noise. And the third key is IQ modulator for advanced modulation format like a QPSK and 60 CAM. And fourth key is a heterodyne detection with a subharmonic mixer for high sensitivity terahertz detection. The bottom left shows a comparison of phase noise spectrum between the f-rep and f terahertz. Due to the phase locking of f-rep to an optical reference of the fiber interferometer, the ultra-low phase noise is achieved in f-rep and then is successfully transferred to the terahertz wave without degrading the optical comb's characteristic. As a result, so we achieve the minus 100 dBc per hertz phase noise, which is not possible with a traditional electric frequency multiplier. Lower right shows a relation between the data rate and the EVM, which is a quality factor of data transfer. So we combine the error-free transmission up to the 84 gigabps with the QPSK and 100 gigabps with the 60 CAM. So this marks a world record in this frequency band. This demonstrated the strong potential of the microcomb for the future photonic 6E. Okay, let's move to the first topics. Research topics. So the first topics is dual-com biosensing for rapid detection of SARS-CoV-2. Go to background. The current standard for testing of SARS-CoV-2 is PCR. PCR benefit from selective amplification of nucleic acid sequence of target gene. However, it has a drawback of long examination time, complicated multi-step analysis, insufficient accuracy, and requirement for skilled operator. If the testing is largely simplified and shortened, it will be a powerful deterrent to the spread of COVID-19. So, as well as a future emerging and re-emerging infection disease that's expected to cause a new pandemic in the near future. So the optical biosensor is a potential method for rapid detection of SARS-CoV-2 due to their sensitivity, cost effectiveness, versatility, ease of testing, and point of care prospect. So the one representative is a surface plasmon resonance, or SPR, like here. So in SPR, when a monochromatic laser light is into a glass prism covered with a metal thin film at the total reflection angle, the induced evanescent wave is coupled with a collective vibration of free electron in the metal, namely surface plasmon. This results in conversion of light energy into surface plasmon energy. When a reflective light is measured with respect to the incident angle, it is sharply decreased at this resonance angle like here. This is a SPR dip. Since this SPR deep shift depends on the sample Ri via the electric field induced by the surface plasmon. It enables a sensitive measurement of sample Ri. Furthermore, if the surface modification is made in the sensor surface, antigen-antibody interaction change the effective Ri near the sensor surface. It means that the SPR act as an optical biosensor. However, the remaining challenge is that the broad SPR deep and its small shift limits the sensing performance. We consider a point for the highly sensitive optical biosensing is that the Ri-dependent or antigen-dependent optical spectral shift should be transformed into a photonic radio frequency signal with a sharpened spectrum. The resulting electric frequency signal can be precisely and rapidly measured by a high-performance frequency measurement apparatus. To this end, we introduce two keys into the optical biosensor. The first key is a combination of optical frequency cone with a fiber biosensor in the cavity, enabling a photonic radio RF biosensor or electric frequency reading optical biosensor. The second key is active damping compensation of temperature drift of sensor signal by using a dual-com configuration. Previously, I said that the OFC can work as a frequency converter or frequency gear from optical to electric frequency. However, in this research, we replace this optical frequency standard into the optical fiber sensor. So in this case, the optical spectral shift of nu M caused by the fiber sensor can be transformed to an electric signal of FREP based on this equation. In this case, the OFC can be used for the photonic radio frequency fiber sensor, which benefiting from a matured technology of electric frequency measurement, such as RF frequency standard, high precision, wide dynamic range, rapid, and cost-effective. We apply this concept for the optical biosensing of SARS-CoV-2. We here use multimode interference or MM fiber sensor for the optical biosensing. MM fiber sensor is composed of craftless multimode fiber together with input and output single mode fiber at both ends. The incident light is diffracted, repeats a total reflection, and go towards the output SMA. Only the light satisfying this equation, namely MMI wavelength or lambda MMI, can pass through the MM fiber sensor. Furthermore, the Guth-Hessian shift at the boundary between the sensor surface and the liquid sample or depend on the sample Ri. In this way, since lambda MMI is a function of sample Ri, MM fiber sensor work as Ri-dependent tunable optical bandpass filter. We next place this MM fiber sensor inside the fiber OFC cavity, like here. Next slide shows the principle of operation for Ri-dependent FREP change. There are two keys. The first key is intracavity MM fiber sensor. In this case, in this key, the sample Ri change is converted into the optical spectral shift of OFC. The second key is the dispersion of refractive index in fiber OFC cavity, like here. In this key, Ri-dependent optical spectral shift of OFC is converted into the Ri-dependent shift of the optical cavity length, or NL, NL, right here. So finally, as the FREP is given by this equation, The sample RI change is read out as a FREP shift. In this way, the FREP reading RI sensor or RI sensing OFC can be achieved. We next place this surface. We next made the surface modification of scope 2 on the sensor surface. Okay, so we first perform the RI sensing of ethanol solution. Ref shows the RI-dependent shift of optical spectrum. Unfortunately, such RI-dependent optical spectral shift is much smaller than the optical spectral bandwidth. Conversely, in RI-dependent shift of RF spectrum, sharp spectrum of FREP appear and its shift is much larger than the RF spectrum bandwidth. As a result, we achieve the RI resolution of 10 power minus 6. So we next make the surface modification of SARS-CoV-2 antibody on the intercavity sensor surface. For the optical biosensing of SARS-CoV-2, we use an antigen-antibody interaction of SARS-CoV-2 protein. Among the several proteins in the SARS-CoV-2, we selected the nucleocapsid protein or N protein due to the abundant existence, low mutation introducing probability, high specificity, sensitivity, and stability. We made the surface modification of N protein antibody on the sensor surface via the SAM layer. Then the OFC light induce evanescent wave near the sensing region. If the N protein antigen is combined with corresponding antibody, like here, OFC light influence depending on the antigen concentration. Then we place this MMI fiber biosensor in fiber OFC cavity. Here, the third key is antigen-antibody interaction. The concentration change of the target antigen is converted into the effective RI change near the sensor surface by selecting a combination of a target antigen with an antibody. Corresponding antibody. The following procedure is similar to the RI sensing OFC. Finally, so we can achieve the FREP reading optical biosensor or biosensing OFC. The remaining challenge is the temperature drift of FREP. Because the FREP are sensitive to the thermal change of optical cavity length as well as the sample concentration change. Right shows a temporal fluctuation of FREP and the cavity temperature when a sample concentration is constant. Temporal behavior of FREP1 clearly indicates the dependence on the cavity temperature with a sensitivity of 400 Hz per degree. Since such a temperature drift of FREP is larger than the FREP shift caused by the sample concentration change, it reduces the accuracy and reproducibility of biosensing as a temporarily fluctuated background signal. To suppress the temperature drift, we focus on the active damping compensation, which is often used with the strain sensing. Let's show the schematic drawing of dual strain sensors. A part of strain gauge is used for the active. A pair of the strain gauge is used for the active and dummy sensor, respectively. The active strain gauge measures both the temperature and the strain, whereas a dummy strain gauge measures only the temperature. If the temperature change of the active and dummy strain gauge is common to each other, differential signal between active and dummy strain gauge is corresponding to the strain signal independent of temperature drift due to the canceling effect of common mode temperature change. We apply this active dummy compensation for the FREP reading optical biosensor by using a mechanical sharing dual fiber OFC. Dual COM configuration. A pair of OFC biosensor is used for the active and dummy OFC sensor, sensing OFC respectively, in which the active sensing OFC measures both the sample concentration change and the temperature change, whereas the dummy OFC sensing measure only the temperature change. If the temperature change is common to each other, differential signal between the active and dummy OFC, so the delta FREP or FREP1 minus FREP2 is corresponding to the sample concentration change, concentration independent of temperature drift in the same manner as dual strain sensors. To confirm the validity of this approach, we first performed the dual COM alloy sensing. We use a pair of linear OFC cavities mode-locked by a subsatural absorber mirror. A pair of MMI fiber sensor is prepared for an active and dummy prepared for the active and dummy sensor, respectively. The active MMI was placed inside the sample cell filled by a test sample of glycerol solution, whereas the dummy MMI was placed inside another sample cell filled by a reference material of the pure water. One cavity with active sensor is used for the active sensing OFC. Another OFC cavity with a dummy sensor is used for the dummy sensing OFC. For mechanical sharing, dual fiber OFC configuration, a pair of fiber OFC cavities were arranged in an aluminum box covered by an insulated material so that they were affected by a similar temperature drift. FREP1 in the active sensing OFC and FREP2 in the dummy sensing OFC were measured by a RF frequency counter synchronized to the Lubizim frequency standard. Finally, the frequency difference between them, namely delta FREP, was calculated as a final sensor signal. We performed the alloy sensing of glycerol water solution. Left shows a sensor gram of FREP1 and FREP2 in which the sample concentration and alloy change as a step-like behavior. FREP2 of dummy sensing OFC depend on only the temperature drift, whereas FREP1 of active sensing OFC depend on both the temperature drift and the sample alloy change. Then we calculate the frequency difference between them as a delta FREP. Right shows the sensor gram of delta FREP. The temperature drift disappear, and the step-like behavior of sample alloy change clearly appears in the sensor signal. So the active dummy compensation extract only the alloy-dependent delta FREP shift without temperature drift. Next, we modify the experimental setup for dual COM biosensing. A modification part is here. A pair of MMI sensor with and without antibody modification is used for the active and dummy sensor, and then they were placed in the same cell filled by a SARS-CoV-2 N protein antigen solution. We perform the rapid detection of SARS-CoV-2 N protein antigen. Left shows the sensor gram of FREP1 and FREP2. Molar concentration of SARS-CoV-2 N protein antigen was changes from PBS 1 attomolar, 1 femtomolar, 1 picomolar to 1 nanomolar as a step-like behavior. In this case, unfortunately, the temperature drift spoils the target-dependent FREP1 shift as a large background signal. However, if the frequency difference between them is calculated, the large background of temperature drift is effectively reduced, and the sample concentration dependent shift appear as a step-like behavior. In this way, the delta FREP reflect only the antigen concentration change. From this sensorgram, we obtain a relation between the antigen concentration and the delta FREP shift indicated by red plot. To investigate the validity of this experimental plot, we perform the curve fitting analysis with the sigmoidal curve. Because because the antigen-antibody reaction is biosensor is represented by sigmoidal behavior. As a result, the good fitting result was obtained indicates the validity of this sensing result. From the curve fitting result, we obtain the sensing performance of dual-cone biosensing highlighted by a yellow color. Yeah. So the limit of detection was 38 attomolar. Linear range was 34 attomolar to 2.1 picomolar, and the testing time is only 10 minutes. For comparison, the sensing performance of other testing methods, including of SARS-CoV-2, including a PCR and other biosensor, is summarized. Only the dual-cone biosensing can achieve the both high sensitivity and short testing time. Let's move to the second topic. The second topic is a dual-cone microscopy, which is application of optical cone for the scanless confocal microscopy. Go to the background. The confocal laser microscopy, or CLM, has been widely used for the biomedical imaging and industrial surface topography. In CLM, using a confocal optics composed of objective lens and a pair of the pinhole, only a light from a focal plane of the objective lens can pass through a confocal pinhole. This results in the 3D spatial resolution with micrometer depth selectivity. If the focal spot is mechanically scanned, the optical sectioning 2D image and the 3D image can be obtained like here. The remaining key for the advanced CLM is the scanless imaging instead of mechanical focus scanning for rapid imaging, as well as image contrast based on the optical phase, in addition to the optical intensity, enabling the surface topography in nanometer and visualization of transparent or non-fluorescent sample. Another image contrast in optical microscopy is optical phase, giving information on refractive index, optical thickness, or geometrical shape. Conventional phase microscopy, such as the digital holographic microscopy, or DHM, can be used for the transparent non-fluorescent object or reflective object with nanometer unevenness. However, in such a phase microscopy, phase wrapping always occurs every 2 pi, making it difficult to visualize the surface roughness beyond the half wavelengths, making it difficult to visualize a thick specimen. So CLM gives the optical amplitude contrast with axial resolution of wavelengths, whereas the DHM gives phase contrast with axial resolution of sub-wavelengths. In this way, the CLM and the DHM are complementary to each other. So if we can combine these features in the same optical configuration, it gives a much contrast of optical intensity and phase and enables a seamless integration of confocal and amplitude image. To this end, we focus on the OFC again. Previously, I said that OFC can be used for the optical frequency ruler or frequency gear. But here we focus on a new feature of OFC, namely an optical carrier with a large number of discrete channels. We propose a third application of OFC, like here. The measured physical quantity is encoded on each OFC mode by dimensional conversion. The resulting dimensional conversion OFC can be used for an ultra-precise ruler for the physical quantity. Mode-locked OFC spectrum is acquired by mode-resolved OFC spectrum is acquired by a dual-cone spectroscopy or DCS. Finally, the physical quantity can be decoded from the OFC spectrum. In this application, the COM spectral line width and number of COM mode line widths and the COM mode spacing are respectively corresponding to the length of the ruler, number of scale marks, resolution of the ruler, and the interval between the scale mark. To confirm this concept, we set the 2D space as a measured physical quantity. In this case, the 2D space or image pixel information is encoded onto the each OFC mode by dimensional conversion between the 2D space and wavelengths. The result is the image encoded OFC. So the image information is decoded from the model resolved spectrum of the image encoded OFC. In this case, the discrete channel number of COM mode line width, and COM mode spacing are respectively correspond to the digital image pixels, sub-megapixel resolution, ultra-high fine spatial sampling, and uniform spatial sampling. The first key of such approach is the 2D spectral encoding of OFC. After passing through a light source pinhole, the input OFC is fed into the 2D spatial disperser. The 2D spatial disperser specially develops the OFC mode into the 2D space, depending on the wavelength, namely 2D spectrograph like here. Then this 2D spectrograph is focused onto a sample as a 2D array of focal spot by an objective lens. Image information is encoded on each OFC mode. Reflection light from the sample or inversely propagates the same optics, and each OFC mode are spatially overlapped again. Finally, after passing through the detection pinhole, the image encoded OFC was obtained. This image encoded OFC establishes a one-to-one correspondence between the OFC mode and the image pixel. Furthermore, a combination of the 2D spectral encoding with confocal optics achieves the compatibility of full-field imaging and confocality. The 2D spatial disperser is composed of Viper and diffraction grating. Viper is a tilted Fabry-Perot like here, and its transmission rate has a resonance transmission peak with a constant frequency spacing equal to FSR, similar to the usual Fabry-Pellot ethanol. The incident lights experience a different number of internal reflection in Viper depending on the vertical position. As a result, a deeply tilted virtual wavefront is generated along the vertical direction. The resonance transmission spectrum slightly shifts depending on the vertical position without the change of FSR like here. To separate this spatial overlap to Viper transmission peak, a diffraction grating was used, resulting in the generation of 2D spectrograph of Viper transmission peaks like here. Finally, the 2D spectrograph is specially developed as a zigzag line like here, from shorter wavelengths to the longer wavelengths. Also, we can observe the image encoded OFC. Spectrometer cannot directly read a finely spaced line of optical frequency cone. In F-rep, if F-rep of OFC around 100 MHz can be correctly downscaled into the 1 kHz by this downscaling factor, a replica of OFC appears in RF region, namely RF cone. Such RF cone is directly readable by usual RF instruments. To achieve the frequency downscaling by ratio of 10 power 5, we use dual-com spectroscopy. The dual-com spectroscopy, or DCS, is analogous to the FTS. However, due to the automatically time delay scanning, it benefits from rapid, high resolution, and high accuracy. In DCS, a pair of OFC with a slightly different F-rep is used for the signal cone and the local cone with a F-rep 1 and F-rep 2 respectively. Frequency difference between them is a delta F-rep. A signal cone passes through the sample and then interferes with the local cone. Lower shows a timing chart of signal OFC cone and the local cone and the interferograph. Since the time period of signal cone is slightly different from the local cone, that of local cone overlapping timing between them slightly is shift every pulse like here, namely asynchronous optical sampling. Such asynchronous optical sampling interference generates an interferogram in RF domain region. In other words, the time scale of signal cone is temporarily magnified by this ratio. Since this temporal multiplication factor achieved to 10 power 5, the resulting slowdown signal can be directly acquired by usual oscilloscope without the need for the mechanical time delay scanning. DCS is a kind of Fourier transform spectroscopy here. But there are no need for mechanical time delay scanning by stage due to the non-mechanical time delay scanning of SOPs. Therefore, DCS is equivalent to a Fourier transform spectroscopy with ultra-fast stage scanning over long range, over 1 kilometer speed at 1 kilometer length at 1 kilometer per second speed. As a result, key feature of DCS includes a spectrometer-free, high resolution and high accuracy, high speed measurement, and simultaneous detection of optical amplitude and phase. Next slide shows the principle of operation for the scanless confocal amplitude and phase imaging. The image encoded OFC has a one-to-one correspondence with image pixel, and all focal spot has a confocal volume like here due to the combination of 2D spatial dispersion and confocal optics. DCS of the image encoded OFC gives a model resolved spectrum of amplitude and phase, which are used for the reconstruction of the confocal amplitude and phase image based on the one-to-one correspondence between the OFC mode and the image pixel. Next slide shows the experimental setup. We use a pair of model fiber laser at 1.5 micrometer. F-rep and delta F-rep are set to around 100 megahertz and 1 kilohertz respectively. The signal OFC can pass through the light source pinhole and fit into the optics for 2D spectral encoding, and is focused onto a sample as a 2D array of a focal spot. Reflected light propagates the same optics and passes through a detection pinhole. Finally, the image encoded OFC is interfered with a local OFC to generate the interferogram. After acquiring the interferogram, we perform the Fourier transform of the interferogram to obtain the model resolved spectrum. The first sample is a test chart with a positive pattern. In the test chart, a reflective chrome coating is made on a glass plate like here, so therefore the chrome coating makes a 2D distribution of reflectivity and phase change reflecting the chart pattern. Next shows the model resolved amplitude spectrum and the phase spectrum for solid coating area and the pattern coating area. Fine structure inside the amplitude spectrum indicates the resonance transmission mode of Viper. Spectral difference between them, so here and here, or here and here, reflects the 2D image information of the test charts. Then we reconstructed the image from this spectra based on the one-to-one correspondence between OFC mode and the image pixels. Left shows a resulting confocal amplitude and phase image. For comparison, we also acquired transmission image of the sample area of the test chart by an infrared camera. These three images were in good agreement with each other. However, the image contrasts were different to each other. The confocal amplitude image reflects reflectivity of the test chart, and its contrast is inverse to the transmission image. On the other hand, the phase image contrast is caused by the thickness of pattern coating, and the difference of complex refractive index between the coating area and the glass. The spatial resolution for these image were at 12.4 micrometer for X resolution and 2.5 micrometer for Y resolution, Y dimensions. Also, the phase resolution was 28 milliradian, which is less than 1% of the wavelengths. We next confirm the confocality by moving the test chart along the axial direction. Both images increase the image contrast within the focus, whereas they disappear out of the focus. From the amplitude image, the confocal axis resolution was 61 micrometer, which is limited by a low numerical aperture of the objective lens rather than the performance of DCM. We also demonstrate the kilohertz confocal amplitude and phase imaging of moving test chart without any image accumulation. In this case, we can increase the imaging rate up to delta FREP, namely 1234 Hz in the present setup, which, although the image contrast was decreased, the behavior of moving test chart was still confirmed. To demonstrate the potential of biomedical imaging, we apply the DCM for the fixed cell sample like here. Since the cell is transparent, confocal amplitude image did not indicate the cell distribution. However, due to the sensitivity to the optical thickness or reflective index, the confocal phase image clearly visualizes the cell distribution. Although the image quality is less than the conventional phase microscopy, but the phase image with the depth selectivity is big advantage over the conventional phase image. Next, we demonstrate the real-time imaging of swimming parameter. We set the frame rate to be 100 Hz. Swimming of the parameter by regular movement was clearly visualized by the confocal amplitude and phase images. In particular, the phase image will give the information on the internal structure of the parameter in swimming. Finally, we demonstrate the surface topography of nanometer step surface. We made the three-step structure on a silicon substrate, and its surface covered by the gold thin film. The confocal amplitude image gives an image contrast only at the edge of the step because of no difference of reflectivity among the step surface and insufficient confocal axial resolution. However, the confocal phase image clearly visualize the difference of the step surface as a quantitative phase value. Then we reconstruct the surface profile of the sample from the confocal amplitude image. The determined step height was in agreement with that by AFM. Finally, we summarize the present talk. We demonstrate two applications of the OFC. The first application is novel biosensing via the optical to electric frequency conversion, enabling a rapid and highly sensitive SARS-CoV-2 detection. The second application is demonstration is a dual cone microscopy with a dimensional conversion optical cone. By converting the optical frequency information into spatial domain, we achieve the scanless confocal imaging of both amplitude and phase. This approach will expand the role of optical cone towards a universal platform for multidimensional measurement. It demonstrated the new application of optical cone beyond the traditional methodology.